Hi everyone, this is Mrs. Jackson and this is part 3, Stretch and Compression of Functions of Chapter 1, Section 2. Recall that this section is entirely about transformation of functions, and unlike the first two that we talked about, translations and reflections, unlike those, stretch and compression results in an image that is not congruent to its pre-image. Okay, so let's get started. The first thing we're going to talk about is in the vertical dimension. So when we take a function and we grab it and we make it taller, we stretch it taller, or we push it down and make it shorter in the y dimension, we call that vertical stretch or vertical compression. And I think it's intuitive to think that if you're going to make your output bigger or you're going to make your output smaller, then we're going to multiply our output y, and I'll just put output here, parentheses. We're going to multiply that output by some kind of stretch factor. Now, the stretch factor can also be the same factor for compression. And in general, we're going to use the variable lowercase a to represent that factor. Okay, so the first thing we're going to talk about in the vertical dimension is vertical stretch. And that means our output is getting bigger for a given input. And so we're going to multiply our pre-image by some kind of factor a, so some kind of pre-image function. And it makes sense that a is going to need to be bigger than the number 1 if we want to grow that output for a given input. Conversely, if we want to shrink something in the vertical dimension, we call that vertical compression. Or you could call that shrink too, I guess. And it makes sense that if we want the output to get smaller, our factor a is going to have to be less than 1. Specifically, a is going to be less than 1, but greater than 0. So if we're going to multiply by some kind of fraction, it makes sense that our output is going to get smaller. Okay, so how does that look on the coordinate plane? Let's do some sketches here. So let's pick an example here. I'm going to pick just our absolute value parent function here. I'll draw it. So I'll call this f of x equal to absolute value of x. And if I want to stretch that up and have for a given input a greater output, I'm going to put that in red, then I'm going to multiply that f of x by some kind of factor. So let's just say g of x equals 2 times our original f of x, or 2 times the absolute value of x. You can see here that for a given input here, my output on the image is going to be much greater than the pre-image output. Another way to think about vertical stretch is that the new image function is getting taller and away from that x-axis. So see how it's moving away from the x-axis. That's going to show you that you're moving taller in the vertical dimension. So let's go ahead and label this stretch. And you can see here in our example that our stretch factor a equals 2. Okay, now what does compression look like? So if we compress, that means we're going to get closer to the horizontal axis here, the x-axis. So I'm going to call this h of x, and I'll make some kind of stretch factor that's less than 1. So I'll just pick a half. So you can see in this example, so for a given input on our original pre-image function, our transformed function, h of x, has a lower output. So instead of getting taller, it's actually getting shorter in the vertical dimension. And let's go ahead and label this compression And in this case, our a factor, our stretch factor, is equal to 1/2. Okay, so what will happen then if we stretch or compress in the horizontal dimension instead of the vertical dimension? When we make a function get wider or skinnier in the x dimension, we call that horizontal stretch or compression. And in this case, we're going to multiply the x variable by some kind, or we should say the input variable, by some kind of factor a. So if we want to stretch horizontally, that means you're going wider. Stretch horizontally. We're going to multiply our input. So if I've got g of x, I'm going to multiply my input x by some factor. And in this case, if we want to go wide, that factor is going to be greater than 0 and less than 1. Let's actually write here wider. And in terms of compression horizontally, that means we're getting skinnier in the horizontal dimension. So that would result in some kind of image where we again multiply our input variable by some kind of factor. But if we want to get skinnier, that factor is going to be greater than 1. Let's actually call this skinnier. Okay, so let's take a look at some kind of graphs here for examples. So if I start out with some kind of function, f of x, instead of using the parent function, I think I'm going to start with something a little different. Let's go with a quadratic that's just shifted up a little bit. So I'm going to call this f of x equals x squared, which is the parent, and I'm just going to shift it up by 2 units here, for example. That'll be a 2. Okay, so we're going to start with a pre-image of a quadratic, and now let's transform this both horizontally. We'll do horizontal stretch, and we'll also do horizontal compression. So if I want to do horizontal stretch, that means it's getting wider. And so let's take a look at an example here. If I want to go wider, kind of go like that. I think I called that g of x. So let's say g of x is going to equal a multiplication factor a times our input, and I'm going to just come up with, say, 1/2. So if we want to go wider, then we're going to have to multiply that input by a number that's greater than 0 but less than 1. So let's take a look at that. G of x equals our original factor here, x squared plus 2. Wherever I have an x, I'm going to be replacing that x here with 1/2 of x. So we'll go ahead and do that. I'll just put x over 2. That's the same thing as 1/2 x squared plus 2. So this green function here, g of x, equals x over 2 squared. I'm going to go ahead and do that square. So that's x squared over 4 plus 2. So that's our green function here, g of x. That is an example of horizontal stretch. And let's go ahead and just label that stretch so that we can see that. Okay, now how about horizontal compression? That means we're going to get skinnier. In that case, I'll draw something in here in red. And these are just sketches, so they're not perfect by any means. So let's call this red function h of x. And if we want to compress horizontally, that means we're going to take that original function f of x and we're going to multiply it by some kind of factor that's greater than 1. So let's just pick 2 as an example. That means anywhere where I have x in my original function, I'm going to replace that with 2x. So if I do that, I've got h of x equals x squared. I'm going to replace that with my 2x and then square it, plus 2. That doesn't look like a 2. And I'll just go ahead and simplify this. 2x squared is 4x squared plus 2. So let's go ahead and label this compression. I'm running out of room here. Okay, so one thing I want to note here before we close out this page is that there's certainly a relationship between vertical stretch and horizontal compression, as well as vertical compression and horizontal stretch. And that's why I kind of color-coded these in a way. So vertical stretch, that means you're stretching taller, but when you stretch taller, you're also getting skinnier. So this red absolute value is getting taller, but it also got skinnier in the horizontal dimension. And so vertical stretch and horizontal compression are very much related to each other when we're using functions that are symmetrical. Now, if you have a function that's not symmetrical looking, they wouldn't necessarily be related. But when they are symmetrical, you're certainly going to see a relationship there. And because of that, it does cause some confusion when you're trying to determine, is it vertical stretch or is it horizontal compression? Sometimes it's both. And likewise, vertical compression here, we're getting wider on this absolute value. We're getting basically shorter, but in doing so, it's getting wider horizontally. Well, that certainly has a relationship to horizontal stretch. So when you're stretching out wide horizontally, that looks an awful lot like vertical compression. And so that's why I put those both in green. Okay, let's take a look at two examples. One example is going to be vertical compression, and another is going to be horizontal stretch. Two different functions that we can take a look at. Okay, so the first one is vertically compressed f of x. It is a transformed quadratic, and we want to vertically compress that by half. Let's first start out by taking a close look at f of x. F of x is a quadratic. It's the parent, but it's shifted down by 6 units. So let's go ahead and sketch that. It's just a quadratic. My sketch is not great, but we're shifting that vertex down by 6 units. So this is our f of x equals x squared minus 6. All right. Let's now look at what we're being asked to do here. We want to vertically compress, vertical compression, by half. Okay, vertical compression, as soon as you're talking about vertical, we're talking about the output, y. So we want to multiply our output by some kind of factor, a, and if we want to compress, that a is going to have to be a fraction, less than 1 but greater than 0. In this case, if we want to compress by half, our a is going to equal 1/2. So if we take a look at g of x, we're going to multiply f of x by a half. F of x is x squared minus 6. I'm going to substitute that in and then simplify. I'm going to by distribution. So 1/2 x squared minus 3 is going to be our new transform function. Okay, so what will this transformed function look like? So we've got a quadratic that's shifted down by 3 units. So I'm going to have a vertex here at y equals -3. But the x squared term is being multiplied by a fraction, in this case a half. That means that portion is going to have a smaller output, which is going to have the effect of making the graph wider. So our new transformed function is going to be wider than the original, and it's going to be shifted up. Now, these two particular functions are going to have the exact same x-intercepts, and I will just defer that for a moment. I haven't taught you how to find those yet, and we are going to be doing quite a deep dive on that in chapter 2. But for now, just recognize that when we transform this function, we are going to have a wider parabola here, and it's going to be shifted up. So let me just label this here, g of x equals x squared over 2. That's the same thing as 1/2 times x squared minus 3. Okay, let's look at a second example, and this time we're going to look at horizontal stretch. As soon as you see that word horizontal, horizontal is the x dimension, the input. So we're going to be multiplying the input by something, okay? If we want stretch by a factor of 3, then let's call this h of x is going to be our original function f of x multiplied by some kind of factor. In this case, if we want to stretch it horizontally, that factor is going to be a fraction. I know that's somewhat counterintuitive, but it's going to be greater than 0 and less than 1. So if we're stretching by a factor of 3, that means that stretch factor a is going to equal 1/3, because it has to be a fraction to get that wider. Whoops, that's a half. It has to be a fraction here in order to get that wider stretch in the horizontal dimension. Okay, so if we take a look at our function here, we're going to take our h of x, and anywhere where we see an x, we're going to be replacing it with 1/3 x, because we're going to be evaluating f of 1/3 x. So we've got h of x, and we're going to replace our function here. In this case, it's an absolute value function. I'm going to put in the absolute value, x over 3. That's the same thing as 1/3 x, and then add 1 to complete our function. Let's take a look at what that would be for the graph. So the first original function, f of x, is some kind of absolute value function, and the output is shifted up by 1. So we're going to have a v here. My pen. So we've got a v going up like this, shifted up by 1. That's the number 1. And when we do our horizontal stretch, that's going to make it wider. And so in this case, our vertex did not change in our function. So we still have that 1, but we're going to get much, much wider here because we're multiplying the output by 1/3. So very, very similar to vertical compression is related to horizontal stretch. So our h of x here equals the absolute value of x over 3 plus 1, and our original function is f of x equals the absolute value of x plus 1. And so this is an example of horizontal stretch. All right, so I want to conclude this video by looking at some examples of compression, both vertically and horizontally, stretch both vertically and horizontally, look at one function, and look at things purely algebraically off the coordinate plane. So let's start out with compression vertically. So if I zoom in here, we're going to start with a pre-image or a input function f of x. It's a quadratic, 2x squared minus x plus 5. And we want to compress that vertically by a factor of 2. Remember, vertical compression, anything to do with vertical, we're talking about our output, our y dimension here. So if we want to compress, that means make it small. So g of x is going to be some kind of scale factor times our input function, where a is going to be a fraction because we're making that output smaller. In this case, if we want to compress by a factor of 2, a is going to equal 1/2. So we've got g of x equals 1/2 times f of x. G of x equals 1/2. I'm going to multiply that half by the entire function f of x, so I'm going to use parentheses here. 2x squared minus x plus 5. And then I'm going to distribute that 1/2 to all the terms in the parentheses. So 2x squared times 1/2 is 2x squared over 2. That'll simplify to just x squared. Distribute the 1/2 to the negative x, and that's going to be minus x over 2. And then distribute the 1/2 to the 5, and that's going to be 2.5 or 5/2. Okay, let's stay on the vertical track here. So let us stretch this time vertically. Instead of compressing vertically, we're going to stretch vertically. So again, vertical means output. And let's call this, well, we'll stay with g of x, I guess. So g of x is going to equal some kind of scale factor times our original function, f of x. This time, if we want to stretch vertically, that a is going to be bigger than 1 to make the output larger. And if I'm going by a factor of 2, that means my a is going to equal 2. So g of x is going to equal 2 times my original function, f of x. G of x is going to equal 2 times my original function, 2x squared minus x plus 5, or 4x squared. I'm going to distribute that 2 to everything now, minus 2x plus 10. Okay, let's move on to compressing horizontally and stretching horizontally. Remember, compressing horizontally, that means you're getting skinnier. That has a very strong look, a very strong correlation to stretching vertically, because that's also getting skinnier. So I'm going to keep this in green just to point out to our eyes that these are quite similar. All right, so horizontal compression, I'm going to change to h of x here. H of x is going to equal our original function in some kind of multiplication factor a times our input. Why input? Because anything to do with horizontal is our x dimension. So that's our input variable. So we're going to multiply that input variable. Now if we want to compress horizontally, get skinnier, that a has to be greater than 1. So in this case, if we want to compress by a factor of 2, and our a is greater than 1, our a is going to equal 2. So h of x is going to equal f of 2x, which means anywhere where we see our x in our original function, we're going to be replacing that x with 2x. So I'm going to have 2x squared in here minus 2x, because I'm replacing the x in the original function with 2x, plus 5. And I'm just going to keep simplifying this. I've got 2 times 2x squared. I have to work that exponent first before the multiplication. 2x squared is 4x squared. 2x times 2x is 4x squared minus 2x plus 5. So I end up with h of x equals 8x squared minus 2x plus 5. Okay, and finally, vertical. We first here looked at compression vertically. Compression vertically means you're getting shorter. Well, that has the effect of also getting wider. So that's very strongly related to horizontal stretch. If we stretch in the x dimension, you're getting wider. So these two are related. So if I want to stretch horizontally, I'm going to be anything horizontally. I'm going to be multiplying my input variable by some kind of scale factor. And if I want to stretch that horizontally, that a is going to be some kind of fraction. And in this case, if I want to stretch by a factor of 2, our a is going to equal 1/2. So my h of x is going to be f of 1/2 x, or x over 2. So anywhere in my original function where I see an x, I'm going to replace that with x over 2. So I have got 2 times x squared. So I'm replacing that with x over 2 squared minus x. In this case, it's going to be minus x over 2. I'm replacing that plus 5. And now I'm going to simplify. So h of x equals 2. X over 2 squared, that's x squared over 4 minus x over 2 plus 5. And finally, my last simplification, 2x squared over 4 is the same thing as x squared over 2. So I've got x squared over 2 minus x over 2 plus 5 is my new transformed function. Okay, so in closing on this video, stretch and compression, they can be pretty complicated and they're related, so it's easy to get them confused. My advice is the following. You're going to have to remember the relationships of that scale factor. When is A greater than 1? When is A less than 1? When are you multiplying the output by A? When are you multiplying the input by A? So if you make some index cards or something of that sort to try to get that figured out, it will help you immensely when you are performing stretch and compression. Okay, I hope this video helps.